All right, just recap what we are trying to do. We are trying to use these degenerations of rational maps to study types of questions about these hyperbolic components. For example, the boundedness of hyperbolic components and the boundary of these hyperbolic components. And last time we were in the middle of doing the geometric construction. So the plan for today is to first show you these two finish the geometric construction and the algebraic construction and show that they're equivalent. And then I'll explain some of the subtleties when working with sequences versus families. And then we'll go to more applications, showing some boundedness theorems using these techniques in degree 2, and so on. All right, so let me just give you a quick recap. So last time we talked about, we start with a rational map on the Riemann sphere, and we extend it to a map on the hyperbolic 3 space. And one of the nice properties of this, this extension is that it is conformally natural, and it satisfies this nice derivative control. So the norm of the derivative is bounded by some constant times the degree. Right, so this is an equal continuity result and would allow us to take the limit. All right, and we also talk about this particular function which measures how far the preimage of the 0 is under the barycentric extension. So this is the maximum of y in the preimage of the origin in the Born model. And you measure it using the hyperbolic distance between 0 and 1. Right, and then we have a similar definition for the conjugacy clause. The nth over all possible elements in the conjugacy clause of L of F, L of G. All right, and then one of the nice properties is that this Rf is a proper function on the space of moduli space, on the moduli space of rational maps of degree D. So this, as the conjugacy clause of rational maps degenerates, we want to rescale the metric using this one. And to do that, we fix some non-principal ultrafilter on N, and then we try to construct this ultra limit. So we didn't mention that last time, so let me write down the proper definition. So you start with a sequence of pointed metric spaces. So Xn is the space, Pn is a point in Xn, and Dn is the metric. There is a very natural way to define the so-called ultra limit, which I should denote by x omega, which it consists of all points Xn, where Xn is a capital Xn, such that the distance between Xn and the base point Pn is bounded by, when you divide it out by Rn, this limit exists. So in other words, this limit does not go to infinity. And then of course, you're going to quotient away equivalence relation where xn is identified with yn if, when you compute the different distance xn and yn. Sorry. I think since we're working with d already, so I don't really need dividing by rn. Here, was that a question? Sorry. This outer limit of this distance is 0. All right, and this is naturally a metric space equipped with the metric induced by the sequence of metrics. So any 2 points can be measured simply by the limit of the sequence of distance between them. And it's well defined because of this equivalence relation. And in fact, it's also pointed. And the marked point is the equivalence clause defined by the sequence of this point, the sequence of the base point. All right, and a very special construction of this outer limit is this asymptotic cone. And the construction is very similar, but in this case, we are going to choose a sequence Rn that goes to infinity. And then we take the outer limit of h3, the base point 0, and the metric we're going to put is simply the rescaled hyperbolic metric. And I'm going to denote the outer limit of this simply by R of h for the base point P, and simply just I'm going to use D to denote the metric. Yes. Right. Okay. So an outer filter is non-principal if and only if the okay. So first of all, the outer filter is a probability measure, a finitely additive probability measure on n, taking value only in 0 and 1. It is principal if it is of a form that the probability of any any set is going to be 1 if and only if this set contains a dictator, contains some specified number.
You gave us that example last time.
Yes. And the non-principal is something that is not principal, but it can also be characterized as something that it is an outer filter such that for every finite set, the mass or the probability is going to be 0. Right? So as long as you have a finite set and you have a non-principal outer filter, omega of that finite set is going to be 0.
Is it safe to say that outer filter is non-principal if it's after this measure?
Yes, that's also equivalent. Right, so in this construction, the outer filter is not that, in some sense, it's not that crucial, but as we'll see in the algebraic construction, the outer filter is crucial in order to get some algebraic structure, a field structure. Yes?
How does the limit depend strongly on the outer filter you get?
In some sense, yes, but in some sense, no. For the asymptotic cone, as you rescale the hyperbolic metric, as you can think about the curvature becomes more and more negative. So in the limit, you get some artery. And there is some theorem which says there is essentially only one artery satisfying these certain conditions. So no matter which outer filter you choose, you will always get some artery in the end. All right. This artery is unique, but not canonically unique. I mean, in a sense. You also, it's all right, and okay, so I mean, it is not hard to see that this, the limit that you're going to get is some kind of a tree-like shape, because one nice property of these hyperbolic tree spaces is that if you take any 3 points and then you draw the corresponding triangles, the triangles are too thin. So that means if I look at the 2 neighborhood of any 2 sides of the triangle, that will cover the 3rd side. Right? So now imagine that since this Rn goes to infinity, so a point, 3 distinct points in this limit is necessarily going to go further and further apart. Right? And then we rescale the matrix so that it brings down to something like a unit length. Then as we rescale the matrix, these 2 neighborhood becomes 0 neighborhood. So what happens here is that these kind of situation or these kind of triangles is going to degenerate to something like a tripod in the limit. Right? So, and then this is a well-known fact that this ultra limit or this asymptotic of R3 or of H3 are going to be some R3. So let me just write down what do I mean really by an R3. It means that it's a metric space such that any 2 points are connected by a unique path isometric to some interval in R. All right, so okay, and because of this equal continuity, we can we can take the limit of these barycentric extensions and then obtain a map on this R3, on this asymptotic cone. And the map is the definition of the map is the most natural thing that you can do. Well, what we are going to do is simply send an equivalence clause modeled by this, represented by a sequence of points xn to the equivalence clause of the sequence EFN of xn. Right, and then because the derivative is uniformly bounded, this is well defined. And in fact, this map, let me denote this map by, this should really be a limit. And let me denote this map by f. F is a degree D branched covering. I will not say too much about how to define, there is an axiomatic way of defining a branch covering over R trees, but I'm not going to talk too much about that. And then I'm going to show you some intuition, to give you some intuition about the geometry of this barycentric extension, which sort of gives you a sort of a justification of this statement. But let me also remark that this, I should add one more statement without totally invariant point. And that is very important. And a point is called totally invariant if it is both forward invariant and backward invariant. All right. So the first remark that I want to say here is that this theorem depends a lot on our choice of this R. So if we have a different scale, tau n, and which is much, much bigger than Rn. So let me remark Rn here is this R of the conjugacy clause of Fn that we choose. If we choose a different scale, then we can still do the same construction because we have a O1 bound on the derivative. The map is still going to be well defined, and then you still get some branch covering on the R tree, on the asymptotic cone, but this F will have a totally invariant point. And if you choose this tau n to be much smaller than Rn, but still goes to infinity, then the same construction will give you a branch covering, but with lower degree. Strictly less than d. All right, so this Rn is the correct sort of a scale that you can see all the preimages of F in a non-trivial way. All right. Okay, so let me try to give you some. Yes. That's a good question. I think recently Charles Fufke and Chen Gong, they wrote a paper and then studied exactly like that.
But from your point of view,
For my point of view, since I'm interested in the study of the, like using the contradictions to understand some of the boundedness problems in hyperbolic components. For hyperbolic components, the argument would be by contradiction, and we assume it degenerates, and then we just need to study this limit by fixing a particular algebra filter. It doesn't really matter.
In your remarks, the app discussion of the R sequence, but it's acting on the H tau instead of on H.
Sorry, can you say that again?
In your remark, app is coming from the R sequence, but acting on H tau instead of H bar. Is that what you're saying?
Well, you also need to change the definition of alpha, but it's basically it's the same definition, but now it is acting on H tau instead of HR. So it's the same definition. Maybe I should change the notation because it's not really the same map.
Sorry, so you forget about the dynamics. So the space HR itself, it's still homomorphic to the H tau, or as a space, they're the same.
Yes.
Okay, it's just how, I see which part of the dynamics you're seeing in the room.
So so later on I will talk about something like this. When you try to change a different scale, you should really think about just blowing up at a point. So here, like we're only interested in the dynamics at the scale of Rn. But sometimes when you're working with the degenerating sequences, you have multiple different scales where you can still see interesting dynamics.
But the underlying space is not actually.
But the underlying space, they are all R trees with uncommonly many branch points at every point, so they are all the same, but they are actually different, the different part of the limit. So and later on, we will kind of use this fact, and then this actually comes it's not an artificial thing to consider these different limits. in order to understand, for example, the boundary of the main hyperbolic component for polynomials, you really need this kind of iterative procedure to understand that. So this is also something that I want to talk about later. Yes.
Where are you using the non-principality?
Yeah, if you have a principal ultra filter, then you are essentially just picking up a single H3. And then the ultra limit, I mean, this is also included in Charles Fafke and Chen Gou's paper. These are the Archimedean points, and then we're like when you have a non-principal ultra filter, they correspond to some non-Archimedean setting. Yeah, so I'm going to assume Rn goes to infinity here for now. Well, there is a finite tree, subtree of this asymptotic cone. And away from this finite tree, the map is going to be locally injective and isometric. And on this finite tree, then since you have some branching happening, which I will do. And then the degree is essentially the preimages of a preimage of a generic point, basically.
But the preimage of this finite tree is still finite, or it's?
The preimage is still finite, yes. By finite tree, I mean the metric can be infinite, but it's only finitely many branches. Yes.
So what's the intuition when you use tau n, which is greater less than Rn, the degree will drop?
Well, the reason is, okay, so if the barycentric extension is discrete, then we expect the degree to be d. All right, so then we are measuring this Rn is essentially measuring the furthest distance of the preimage. Right, and then if you ignore that part, if we're choosing just the tau n, then we do not see in particular that preimage, so the degree would jump. All right, and then this was for now we don't know how to prove that this map is a discrete map, but it's the sum of the idea comes in. I mean, this is the intuition here.
So my scale is much smaller, and I'm using something which is of the
Yes.
and the degree jump. But my scale is much larger than Rn, then the whole thing stays in some bounded part which is much smaller, and that's what gives rise to the total invariant point.
Yes, exactly. So if you have tau n is much bigger than Rn, then some point whose preimages are all contained in some. They're going to go to 0 if you divide the distance by tau n.
See all the preimages in a single cluster.
Yes, exactly. Yes.
Does the set of directions at a point have any structure in the tree?
Yeah, we'll talk about that.
Okay.
Thanks. All right, so, okay. I want to give you some intuition about the barycentric extension, so I'm going to draw some pictures. Maybe I'll not explain what I mean by these pictures. I'll try to explain it. Okay, so let's consider 2 points in H3. All right, and what happens is that when you have 2 points in H3, you can connect them by a geodesic. And then you can look at the hyperbolic planes perpendicular to this geodesic passing through these 2 points. So 2 points, a pair of points in H3 correspond to some annulus of the Riemann sphere. So the picture looks something like this. All right, and if you have a Mobius transformation, then it maps circles to circles. So it maps this round annulus to another round annulus. And then the map will simply send the geodesic connecting AY to the geodesic connecting the corresponding 2 points associated to M of this annulus. Right? And this kind of picture is quasi-true if you replace the degree of the map from a Mobius transformations to a degree D map. Right, so what do I mean by that? Well, So if, let's see, A of xy is a round annulus associated with 2 points x and y, and the distance between x and y are sufficiently large. So there is some the lower bound of the constant that we need to put in here. All right, and then let's consider the preimage of this annulus. So we assume that we have another annulus which is mapped to A of xy by a degree, let's say, E covering. All right? So since this A prime is the preimage of an annulus under a rational map, this may not be a round annulus anymore, but it might look something like this. All right? But the modulus of, since we assume the modulus of this A xy is big, the modulus is exactly the hyperbolic distance divided by 2 pi. The modulus of A prime is also big. And there is a classical theorem by Affors or Macmillan which says if you have a large modulus, you can always approximate it by some round annulus up to an OY, up to some like bounded modulus distance. Right? So you can always find some kind of a round annulus that approximates this A prime. And this round annulus, as I explained here, would correspond to 2 points, a pair of points in H3. So this thing here should correspond to 2 points A of AB. Right? And then the barycentric extension would simply send this A 2x up to a bounded amount, a uniformly bounded amount. And similarly with the EF of B to Y. Right? So this tells you like this, this map is sort of like a covering map away from something like a critical locus. All right, and then using this together with some estimate, you can actually prove that this is a degree D branch covering, basically. All right, so that's the geometric part of the story. And let's see. All right, so let me try to motivate the algebraic part. So let's try to understand what does the boundary of this asymptotic cone look like?
Just before you continue,
Yes.
for the E here, where E appears in the extension?
Well, E will, okay, so the modulus of A prime is approximately the E times the modulus of A. So the distance between AB is roughly the E times the distance between XY. Yep. We have it. All right. Okay, so now I want to motivate the connection of this geometric object with some algebraic object. So let's consider this hyperbolic 3 space. So this is a very homogeneous space. So it can be identified with something like SL2C model A as O3. So in the Poincare-Ball model, we have the Mobius maps acting on it, and then the stabilizer of a single point is SO3. But in the Poincaré's upper half plane model, we can also identify this by the space of affine transformations of the complex plane modeled away with S1. Right? And then what this thing is really the space of disks. Right? So around the disks in C. Right? And the picture looks something like the following. So if we have a disk on the complex plane, and we think about the hyperbolic 3 space as the upper half space, then we can draw a hemisphere from that circle, and there is a tip point. And then this tip point is the correspondence between a point in H3 and the disk of the complex plane. Right, so now we are working in the definition of the asymptotic cone, we are working with a sequence of points in H3. So let's just imagine that the sequence of points are convergent to the origin of the complex plane. So and if you compute if I call this the P and Q, and then P corresponds to the bore, or the boundary of the bore centered at origin with radius 1, and Q corresponds to a bore centered at the origin with the radius rho, then this rho, or this hyperbolic distance between P and Q, is simply the integral of rho to 1 of 1 over y dy, which is something like a log of rho. Right, so in other words, so a sequence of points in H3 casts some shadow of disks, and if these 2 points are growing with respect to Rn, these shadows are shrinking with respect to e to the minus Rn. Right, so this is the reason why we're going to define this rho n equals to e to the minus Rn, and this is the correct scale to look at the points on the boundary. And since Rn goes to infinity, this rho n goes to 0, and we are going to consider the sequences of points in the complex plane that modeled by this sequence rho n now. Right? And this is motivates the following definition of called the Robinson's field.
So these two metrics on your, is it a spherical metric? Your rho n is
Let's take it as just the Euclidean metric for now. Yep. All right, so here we are going to define the Robinson's field, and this Robinson's field turns out to be, again, the set of all sequences Zn, where Zn is in C, and these Zn do not grow too fast to infinity. So the limit as log of Zn over Rn is bounded. And then you quotient away with some nice equivalence relation where Vn is identified with Wn if their difference, you take the difference between Vn and Wn divided by Rn is minus infinity. Well, this rho n, this rho is just a reference that we're using rho n in the definition of here, and then rho is related to Rn in this very specific way. And then this was just the motivation of starting using this scale, because this is the scale that you actually see the shadows of these points at infinity. All right. In somewhat surprisingly, this turns out to be a field, and this fact actually requires this we use this ultrafilter. So for example, 0, 1, 0, 1 is a sequence in the complex numbers, but also 1, 0, 1, 0 is also a sequence. The product is the constant sequence 0, and it better be the 0 element. But it seems that none of these things are 0. Right? So it's not even an integral domain, for example. Right? But the reason that it is a field, or is that at least one of these two things is going to be 0. Right? Because the ultrafilter is a finitely additive probability measure. So one of either the set of all even numbers is a small set, or the set of all numbers is a small set. Right? So the ultrafilter picks up which one of them is the 0 element. Right? But not only is it a field, it is also a non-Archimedean field. So this was a theorem proved in the 1960s by Robinson, which studies exactly these kind of a field. But with a small modification, he studied only like in a real setting, but the same definition, the same proof goes in the complex setting as well. Right, so this rho C is a non-Archimedean field. And it's complete. In fact, it's spherically complete. And it is algebraically closed. All right, so spherically complete means that any closed balls, in the nested intersection of closed balls is non-empty. And the non-Archimedean, the norm, or the valuation is simply defined by this limit. All right, and then we can look at the Berkovich space, or the Berkovich P1 of this field. And we denote that by P1 Berk of this rho of C. And it consists of all these classical points, which is just P1 of rho C, union the hyperbolic part. So what are they? I mean, then this is a theorem by Berkovich, which is the well-known classification of the Berkovich P1. The Berkovich space consists of exactly two different types because our variation ring is R and the field is spherical complete. So an element so H Berk consists of exactly, or in correspondence, maybe it is better to say following way. The space of closed disks in all right, so now we can sort of identify this Berkowitz space of the Robinson's field with the asymptotic cone of sort of tautologically, because both space can be thought of as some homogeneous space of some Mobius maps model away some stabilizers. So this H3 or this asymptotic cone can be identified if you really work out all the details, can be really identified with these affine maps. In this field, portion away the stabilizer of, let's say, a closed bore centered at a 0 with radius 1. But this is also the same as the, because of this identification, because of the classification, the hyperbolic space associated to this Berkowitz space.
And what is the meaning of your squiggly isomorphism symbol here? So this is in the metric setting.
Well, I mean, this simply means that we can think about this asymptotic cone as some homogeneous space. I'm looking at an action of the affine space acting on it by the natural extension of the affine group of the complex plane to H3, and then we take the limit, and then we quotient away the stabilizer. And this is exactly what I mean by that. I don't know if you can put a metric structure here, but these two things, you can both put a metric structure on both sides, and then they are going to be isometric. If you choose the same R and then the rho in this particular way. I don't know if that answers the question.
Sorry, did you say you put a metric structure on the Berkowitz space? So it's not compatible with the Berkowitz topology?
No, it does not. It's much weak. I don't know if it's a stronger or weaker. It's one of the two. Any other questions? All right, so.
Sorry, I'm confused by the theorem.
Yes.
H bar equals P1C union H bar. So.
Zero, I think that's what I wrote.
The thing on the right is the P1 Berg C is equal to P1C H Berg and the theorem.
Ah, I see. I don't know if that helps.
I was just misreading.
Yeah. All right, so now I want to, this is probably well known to the audience, but just, I'll quickly go through these, the definition of reduction and the tangent maps, just in case. All right, so okay, so we can consider. So associated to this this non-Archimedean field, we can always consider look at its residual field, which is defined as simply the ball with the radius 1, quotient away with the ball with radius with the open ball with the radius 1. So, and then let's denote this pi, which is simply the map going from a closed ball to K, projection map. And in our setting, this field is still huge. The residual field is still huge. So remark, K is big. All right, so so for example, if we assume this rho n equals to 1 over n, just for concreteness, then this K would contains equivalence clauses of sequences such like log n. Right, so they go to infinity, but it's much slower than any polynomial rate as 1 over n, so its norm is going to be 1. So this K is much, much bigger than the constant sequences, which can be identified with the field of complex numbers. Right? And there is a nice theorem, which is well known, to understand the dynamics of the rational map on the Berkovich space. So, but before that, I should let me mention that now we can, if we have a sequence of rational maps Fn, that means looking at writing in its coordinate, I can write it like something like this. Then I can think about, just recall the coefficients at the sequences. Right, so this gives me a rational map with coefficients in this field, this Robinson's field. A priori, the degree might drop; it might not be d. But it turns out that in this case, the degree is in fact d. And once you have a rational map in this non-Archimedean field, and it naturally extends to a map on the Berkovich space. All right, let me denote this extension by B. So initially, this map acts on P1 of the Robinson's field, and now you can extend it to an action on the Berkovich hyperbolic space. All right, and the claim is that under this identification, these two maps are the same. Right, so you do the geometric construction, and then you look at the asymptotic cone construction for hyperbolic space, 3 space, and the limit of the barycentric extension, or you can regard this sequence as an element in the rational, as an element of a rational map of degree d in this Robinson's field, and then do the construction, and then do the extension. These two maps are the same. All right, so I want to just discuss briefly about this and talk about some of the subtleties here. So first of all, this is a very well-known theorem, which says that if you have a this map fixes the Gauss point, and this Gauss point is the unit disk center at the origin under this identification of the hyperbolic 3 space, the H-Burke with the closed disks of the Robinson's field. This happens if and only if, when we look at the reduction. So let me also give a symbol here. So I'm going to denote this rational map as F. This reduction has degree greater or equals to 1. All right, and then this reduction simply means that we sort of write it in the coordinates, and we make sure that the valuation, the maximum valuation of the coefficients on top and the bottom is 0. And then we do the projection onto the residue field. Right, so this reduction here is some element in the space of rational maps of the residue field. And since we are working with the homogeneous spaces, so if you have any point x, I can write it as some m of xg, and y, I can also write it as L of xg, then the extension sends x to y if and only if, when we look at the reduction of this composition has degree greater or equals to 1. All right, and then we usually call this the tangent map, or dx of B. Sorry for the non-standard notation here. So this map is really going from the tangent space based at the point x to the tangent space based at the point y, which can both be identified with the projective space of the residue field K. And the proof of this equivalence sort of boils down to clarifying like what we mean by sending a point x to y and then sending a point x to y in both different settings. All right. Now I want to talk about rescaling limit and the length spectrum. All right, so first let me give you a definition which was due to Giancili. So here you have a sequence of rational maps with coefficients in C, and Mn is a sequence of Mobius transformations, and we say Mn is a rescaling for Fn, or we're rescaling for Fn if there exists some q, which is an integer greater or equals to 1, such that when we take the outer limit of Mn inverse composed with Fn to the qth iterate composed with Mn, and this has degree greater or equals to 2. All right, so here, when we look at this limit, what I mean is simply just look at the coefficients, the limit of these coefficients, And there might be some cancellation, and then we cancel all the common factors. And if what remains is going to be a rational map of a certain degree, and if the degree happens to be greater or equals to 2, we call that a rescaling limit. Right? One nice thing about this rescaling limit is that this rescaling limit gives rise to periodic points of f on this asymptotic. So, but unfortunately, not necessarily every periodic point of f would give you a rescaling limit, even if the degree is 2, unlike when we are studying the family case. For sequences, this map may not be surjective. So let me quickly mention what do I mean by that and expand it a little bit. So instead of working with the most general setting, let me try to consider a fixed point. This Mn is just the identity.
Excuse me,
Yes?
So there's a question of scale here. So if you scale R is not compatible with the scale Mn, you get different properties of the corresponding periodic point, of the corresponding tangent path.
Yes, so there is a problems with this scale. I mean, this is exactly the reason why you may not get a surjective map here. All right, so let's consider the easiest situation. Where, so let's assume this f fixes the Gauss point. So now my notation is going to be a little bit, okay, so let me try to fix my notation. So I'm no longer going to use B because they're the same. So I'm only going to use f here. So f is this map on the tree. And let's assume f fixes the Gauss point and see what happens. So if we have a rescaling limit, that would mean that Fn, as we take the limit of Fn, this is indeed has degree greater or equals to 2. And this immediately implies that the reduction has degree greater or equals to 2. Right? So, in other words, this condition.
So we assume that you have a rescaling limit, and you assume also that f of x is equal to 2.
Right. So maybe I should change my presentation a little bit. So let me first do one direction. So if we have a rescaling limit, then this means the reduction is also has degree greater or equals to 2, and then by this if if statement, this means f is x. Fixes point. Right? So you have a fixed point. But on the other hand, if the reduction has degree greater or equals to 2, this simply means that if you look at what happens in the barycentric extension, this means that the barycentric extension Fn sends 0 to 0, but this distance is of order O of small rn. Right? On the other hand, having the limit of this sequence, this rational map has degree greater or equals to 2 would mean that the barycentric extension of Fn acting on the origin, the distance between that with the origin is of the order O of 1. Right, so not necessarily you get a from a fixed point. Not necessarily, you might not have a rescaling limit. Right, so one natural question to ask is when is a periodic point a rescaling limit? And one way to sort of understand, yes.
Even in the usual further setting, like the Kiwi setting, I mean, not all periodic points are rescaling.
Yeah, that's true. Yes, that's true.
That's a more basic thing.
That's more the basic thing.
This is, okay, there's some higher degree.
But even if we assume this xg is a critical point, let's say local degree greater or equals to 2, you do not guarantee that. You only know that this distance is of order O of Rn. It does not guarantee that the extension is O of 1. In other words, this residue in the usual setting, the Pearsall series settings, the residue field is C. So whenever you have a reduction, it reduces to C. Here, the residue field is huge, and then when you have a reduction, this reduction may not be a rational map defined over C. And that's the problem. And then, all right, so what should we do? Well, what we can do is to really look at this cascade of these Robinson's field. And that's where like different scales will play an important role. So here, if the reduction has, I mean, for simplicity, let me just assume the reduction has degree greater or equals to 1, then everything is just going to be if and only if statement. So this happens if and only if this, and this happens sort of if and only if this. So then what we can do is to rewrite this Fn as some Gn of z times z minus a1n over z minus b1n times, or maybe there is a product I from 1 to some k. Right, where these two things are getting very close together, so that when you take the reduction, this part goes to 0, goes to 1. So you only note that this Gn part. So in other words, this AIN minus BRN, when you look at their distance in row n, this is less than 1. Strictly less than 1. So when you take the reduction, they go to 1. All right, and then now you have this lift, which is this Gn. And this Gn, you can play essentially the same rule. You can look at this R of this sequence of rational maps Gn. And this will give you a secondary scale. I mean, it's called this tau n. So here are some really simple observation that there exists a rescaling limit with the same degree as the reduction. If and only if this tau n is bounded. Right, so in the case when tau n is unbounded, then you have the, then what we definitely know is that this tau n is much, much smaller compared to the original, the first scale Rn. And then we can continue this process, and then we get another Robinson's field, which sort of, you glue this Robinson's field so that the boundary of this R tree attached to the tangent space of subset, a subfield of the, maybe really a subset, a translation of the subfield of the tangent space. Right, and then, I mean, this is literally some of the subtleties when you're working with the sequences versus families. In the family setting, the reduction is just a C, and everything is nice. And for when you're working with the sequences, you might see various different scales. And you will also see something like this when you're working with the length spectrums. And I will talk about that and then pose a question and think.
Refining your look at F and how it degenerates. So the ANs and BNs are what? So you have zeros and poles that are getting close to each other, but in some Robinson sense,
Yes.
In some metric sense.
Yes.
But then GN, what's left over, can still degenerate without zeros and poles getting close together.
So they're getting close together, but the rate of them getting closer together has modulus 1.
Okay, and modulus 1 is a logarithmic.
Yeah, it can be logarithmic. So if it depends on the first scale you're working with, you might, if the first scale, they might going away with each other. The one way to think about this is really to think about the barycentric extension. Right, so when you have a barycentric extension, some of the preimages is getting very, very far away. So when you rescale it so that you have two different rates of these preimages of a single point. So some of the points escape to infinity as exponential rate. Some of the points escape to infinity at the polynomial rate. And when you're working with the first scale, you bring down the preimage of those exponential rate escape to a bounded distance, right? And then on this scale, you don't see those points as escaping. So in order to detect the secondary extension or secondary degeneration, you really need to look at the reduction map and then do the same thing using the same construction. Right? And in fact, if this tau n actually goes to infinity, assume tau n goes to infinity. Then one can actually prove, and we also assume, let's assume for simplicity that this all of Gn is roughly the same as all of G, the conjugacy clause then really the limit of the barycentric extension for Fn is the same as the barycentric extension for Gn. So previously we have talked about if you rescale your metric in a slightly different way, you might get some branch covering of a lower degree. And here, this is exactly what we're doing here. And then this degree of this Gn is simply the degree of the reduction map. And then what we obtain here is a map of the lower degree. All right. Okay. I really want to pose a question after this. this discussion here. So let me first talk about the length spectrum. And then I want to pose the question, and then I want to comment a little bit more about that. Yes.
In the context of like an algebraic triangle,
Yes.
so does this mean if some zeros and poles are degenerating sort of a polynomially faster rate than some others, then these would be detected as like the exponentially approaching the boundary ones, and then your Gn is encompassing that.
But I think if you're working with algebraic families, you only have one rate. It's always the same rate. Yes, this only happens if you're working with some sequences. But sometimes you're forced to work with the sequences because you don't know how you have a nice algebraic descriptions of your degeneration. So this, and I want to say that you do actually see that in even working with this principal hyperbolic component of like a polynomial. You do see these different rates of degeneration there. All right, so unlike the rescaling limits, so you sort of see the rescaling limits are kind of periodic points of the interior of these hyperbolic parts of the Berkovich space. The length spectrum are associated to the ends of periodic ends of the Berkovich space. So, so what happens here is that whenever you have a sequence, so this is a sequence of periodic points for Fn. So let's assume they're of the same period. Even for simplicity, we might also assume that they're just fixed points. Then they correspond to some fixed point or period P for the rational map defined on the complexified Robinson's field. And one natural question is, what is the multiplier or the length of these periodic points? And it turns out that you can compute this length in two different ways. So Zn Fn is going to be defined as logarithm of the derivative to the qth iterate, and then take the derivative, or the pth iterate, and then you take the derivative. So we want to understand how these length spectrums, or how the length of these periodic cycles behave as we degenerate. And you can compute it in the as a sequence, but you can also compute it as the multipliers associated to the end. So here I'm going to parameterize I of t as a geodesic, or the ends. Not yet. I'm not writing a statement yet, so in the statement there will be a dividing factor. Let's say the end for Zn. All right, and then we can define sort of the length associated to this periodic ends as the limit as t goes to infinity of the distance between a base point. So let me pick a base point. So you should really think about this as going all the way to an end. And then let me pick a big base point A0. And this is the distance between A0 or I of t to x0, a0 minus the distance between f of t and a0. So f of t is somewhere here. Maybe here is to the power of p. This is f of t, and under the dynamics, it may map to something like f of t. And we are measuring the distance between f of t and a0 and f of t with a0. So it is this distance here. Right, it is an easy observation, or you can actually compute this pretty easily, that this length spectrum, or the limit of the rescaled length by Rn is going to be the translation length along the end. Alpha t is just a parameterization, a geodesic parameterization of an n towards Zn. So Zn corresponds to an end of the tree, and then you just pick any ray starting at A0, marching towards this end. It's a geodesic ray going towards the end. And it turns out that this sequence, or this family, or this function is eventually constant. So the limit exists. And this limit is called the translation length associated to this end. I think it should be f of p. Yes. Yeah. Yes. Sure. Sorry. So f of an end, or L of an end of f is the limit as t goes to infinity of the distance between alpha t and a particular base point minus the distance between f to the pth of alpha t to the base point. All right, so one nice corollary of this lemma here is that if L of Zn f is positive, then we have repelling periodic points, and then this periodic cycle along the sequence goes to infinity as a rate of Rn. Then this L of Zn, Fn, they go to infinity as, or maybe they're compatible to Rn. On the other hand, if this L of Zn with f equals to 0, then we can't really say too much, but rather all we know here is that these length spectrums, they are small o of Rn. So they might be bounded, they might still be unbounded. All right, and here is the question that I want to ask. can we find a bound on the number of scales for the length spectrum? Right, so in this case, they might still go to infinity, and then you find a secondary scale. And you might find multiple different scales. But can we find a bound on the number of scales for associated to this length spectrum? I was thinking about this question when we were preparing this talk, and then I realized yesterday that Charles Favre and Yusheng Luo, they almost have a preprint studying exactly like this as this question. I'm Yusheng Luo. And she might get an answer to this question pretty soon. So maybe like next week or next month.
Maybe tonight.
Maybe tonight.
Yeah, she's giving up the.
So one quick observation here is that when the degree is 2, then there is a sharp bound which is 2. And so in degree 2, let me just put a remark. In degree 2, the sharp bound is 2. So in other words, whenever you have a sequence of rational map of degree 2, there exist at most 2 different scales. Rn greater or equals to tau n, which is go to infinity, such that for any p of periodic cycle, of period p, or maybe c, when you look at the length spectrum, exactly one of the 3 would happen. So the length spectrum are either bounded or when we take here this limit, or when you take the limit of this Cfn divided by the first scale is bounded and it's non-zero. Or you have the length spectrum with respect to the second scale is unbounded and non-zero. Bounded does not count as scale for me, no. So 2 different scales to go to infinity. Yes. The hope is the bound would only depend on the degree, and potentially maybe 2d minus 2, or maybe even linear, something related to the degree of the number of critical points.
Why could we do it for d equals 2 and
Well, I was hoping to discuss that in this lecture, but now maybe I have to postpone that for the next one. In 5 minutes, okay, so maybe the short answer is that, so in degree 2, which a lot of good things happens in degree 2, so there is a classification of all, sort of a very satisfactory classification of all the rescaling limit in degree 2 by QE, which says there are only at most 2 rescaling limit. This was wrong. This breaks down in higher degree. And then the second important, and then I mean, pretty much this is the reason why you can have a nice bound in degree 2. Yes?
For this question, instead of sequences, you have families?
The families is always 1. So if you have a degenerating family, the scale is always log of 1 over t.
When you say family, you mean a 1 parameter.
one parameter family, yes. When I say family, I really mean one parameter family. And then the bound is always, it's either bounded, the multiplier either bounded or it's of the order log of 1/t, something like that. So the situation is more complicated, let me just say, for sequences.
What's the simplest example of the short bound for every family? Can you see a quadrilateral product?
Yeah, you can even see this for Blasch products. Okay, so maybe I'll explain that example. I think that I can explain maybe in 3 minutes. And then I want to, in the next lecture, I will probably go really, really fast if you want to talk about all the things that I want to discuss. Or we can sort of like sketch some of the ideas that I want to share here. All right, so okay, so the construction for the two different scales comes from a Blasch product. So B of Z or Bn of Z, I can write it as something like a Zn times, all right, so, okay, so something like Z minus Rn e to the I theta n over 1 minus Rn e to the I minus I theta n Z. Right, so this is a proper map of the disk with the radius of degree 2. So there's only one parameter here, which is this Rn e to the I theta n here. And one can compute the derivative of this is simply, suppose, minus Rn e to the minus I theta n. Oh, sorry, I theta n. Well, at 0, yes. No, otherwise it will be false. So 0 is the attracting fixed point, and the derivative at the attracting fixed point is, you can compute explicitly, is simply this number. Right, so now imagine that as now we have a sequence of these numbers. As you approach to this particular point 1, then the derivative of this at the origin goes to minus 1. So when you look at this, the tree that you're going to build, it has a fixed point at the Gauss point, maybe. And then the first rescaling map is just going to be a rotation with the of 180 degrees.
Okay, so theta is going to 0 and Rn is going to 1.
Yeah, so Rn goes to 1, theta n goes to 0.
So what are your Rn's in your other sense?
It's a different Rn. I think that's a good question. They are compatible. I mean, oh, no. In the hyperbolic distance, they are compatible. So if you look, this Rn, R of a Bn, is compatible to the hyperbolic distance between 0, the attracting fixed point, and Rn. That's it. All right. And then now if you choose your Rn, and Rn goes to 1, and if you choose your theta n carefully, this critical point here is going to map to somewhere here and then comes back. And when it comes back, it really depends on how you approach this particular point 1. If you approach very tangentially, it might miss this particular fixed point. And then you can see that if you approach it from downstairs, the first approaching will go, there is a ribbon structure, so the first approacher is going to be very far away to the left, to the downwards. And if you approach from the top, the first return is going to be very top, on top of this point, particular point. And there must be something in between so that the distance between this critical point and the first return is of order small o of Rn, but it still goes to infinity. All right, so this will give you the secondary scale. All right. Okay, so I think I'm going to stop here, and then I'll continue this afternoon. Thanks.